Hi, folks. I'm going to try to make this as quick as possible here because my computer's been freezing up on me this morning and I want to get this note section out to you guys. This next topic is not going to be the easiest one to convey to you guys as far as using the platform that we are currently using. I would normally bounce back and forth between some simulations and demonstrations and so on, but I'm going to try to chunk this up and just get the notes done, then try to start one with the simulation here in a little bit. I don't know if that was what was causing it to freeze or not, but anyway, we'll see if I can get through this video. All right, so as of this point, we have talked about several different wave characteristics of light. Reflection, refraction. We've talked about dispersion due to refraction, and we've talked about polarization. Today I want to talk about diffraction and how light will bend around a barrier when it comes into contact with that barrier. And then easiest probably apply this to several different types of waves, specifically water waves. Seems diffraction is a little bit easier to visualize and understand in that manner. All right, so when any sort of wave is incident upon a barrier, it will bend around that obstacle or barrier. Okay, so if we're looking at this visual here, and we'll start with this far right one. Notice we've got these two slits. So if we can imagine a water wave coming in, once it hits that opening, the water will propagate outward in a circular manner on the other side of it. Okay, if we increase the width of this opening, we will get this planar wavefront that generates, but we will still see some bending of the water wave as it goes around the edge or the fringe of the barrier. Okay, the easiest way to kind of put this conceptually is in particular when we're looking at the circular wavefront. And I've used the term point source several times during this lesson. If we can imagine just having a bucket of water and then just dropping a small pebble right in the middle of it, it would make sense that the water is going to propagate outwards from that point in a circular manner. So what we will get is these circular wavefronts propagating out. So basically, when the slit width approaches the wavelength of the incident wave, a circular wavefront results. And what we will say is that this behaves as a singular point source. Okay, so once again, if I use that term, just imagine dropping a pebble right here, and we would get these circular wavefronts that would result from that. Okay, I know you love seeing this, but last year we talked about wave interference and the principle of superposition. So remember, we have when we superimpose two or more waves, we end up with either constructive or destructive interference that results from that. Okay, so constructive interference occurs if we take two waves that are perfectly in phase and we overlap them, and we get this super wave that results from it that double the amplitude. This is talking about obviously mechanical waves here, but we will apply this to light here in just a little bit. When destructive interference of waves occur and we get a perfect 180 degrees out of phase, we should end up with no wavefront that propagates out from that point. So we end up with a flat line as far as the energy of the wave that occurs. Okay, so when we're applying this to light, you will see that I will use a couple of terms. We want to make sure our incident light is coherent, so the initial light is in phase. Okay, there are some ways to make that happen, and we'll talk about them maybe later in a video, but right now I just want to make sure you understand this term, is that incident light that is coherent is in phase, and we want the light source to be monochromatic. Okay, we can utilize white light. I will show you that here in a little bit, but it's easier to do the calculations and everything. We are just focusing on one specific wavelength. All right, so explaining this. The AP asked this question a few years ago, and even though this topic isn't on the AP exam this year, I still wanted to go ahead and explain it and talk about it. So why these wave fronts result in the way they do is we can use Huygens principle to explain this. So basically, Huygens principle treats every point as the wave as its own point source. Okay, so we have a common center. So imagine we have this wave that's propagating outward and it's to this point. Okay, so we have a water wave that we dropped our pebble right here. As it gets to this point here, we can now consider points A, B, C, D, and E to be all singular point sources. But by mapping these point sources out, they all have a common center. Okay, so if that results, we will end up with a perfect circular wavefront that propagates outwards. However, if we put points A, B, C, D, and E all in a line and we make them propagate from here, they do not have a common center. So what happens is we have these regions where we have constructive and destructive interference that results, and we end up with this planar wavefront that propagates from that point. Now, notice on the fringes, we still have a circular wave. Okay, we will discuss this later. There is some interference that occurs here on the fringes, but for right now, we just want to understand that there is a circular wave that propagates out from the fringes because of a lack of interference, okay? But there is a minor interference. We'll show that here in a little bit. Okay, this visual shows another example of that, where we have our singular point sources. And as we begin to draw all these waves, and don't worry, you're not going to have to draw anything like this, but as we begin to draw all these waves, we will see these maximum points where they overlap form this planar wavefront here with the circular wavefront formed at the fringes. So I already mentioned this above, but when the slit is small enough to act as a single point source for a wave, then we will end up with a circular wavefront that propagates. So the slit width is equal to or approximately equal to the wavelength. When we get wider slits, we will end up with multiple point sources that interact. All right, so how does this affect and show that light behaves as a wave? So Young's double slit experiment. Instead of using a single opening, he uses two. And he uses a coherent light that basically what he did was he had another single slit back here. So he took light from the sun, used a single slit so that he got just a circular wavefront that propagated from the single slit. What that did is it created coherent light instead of having light in multiple different waves. Basically, it means that all the light was in phase after passing through the single slit. So imagine there's a single slit right here. Coherent light then, he made that incident upon a double slit. So knowing that this light was coherent, the pattern that resulted created several different bright and dark fringes on the screen. Okay, and there's a specific mathematical relationship between those that shows that the wavelength of the light incident upon these slits followed the pattern that created the constructive and destructive interference patterns. Okay, so this point right here, this is called the central maxima. All right, I'll get to this here in a little bit in more detail, but this is something that's important to understand. The distance from this slit opening to this and this slit opening to this central maximum is exactly the same. So if I take a straight edge and I just make a line from here to here and a line from here to here, the distance that the light has to travel is exactly the same, which if this is coherent light, we would expect that the light to be in phase at this point once it gets to the screen. Okay? Now, what happens is on both sides of the central maxima, we have our first dark fringe. So the light comes through here, and when it hits this barrier over here, we have this bright light that shows up in the middle, but then we have nothing that shows up here. This indicates, excuse me, this indicates that the waves are out of phase. The light from this and this slit are out of phase when they get to this opening or this part of the screen and this part of the screen. So that means, as we get into this a little bit later, that the distance that this light has to go from this slit to this part of the screen and from this slit to this part of the screen, now the distances are going to be different. Okay, we will find that this first order minimum is exactly, this distance that the light has to travel is exactly 1/2 of the wavelength difference. Okay, now on the side of the first order maxima, we have our first order minima. Sorry, this is called the zeroth fringe, first order minimum. These brights here on the other side of this is our first order maximums. Okay, so once again, now we have another region of constructive interference that forms where the two waves are in phase when they get to this point. So that means that, once again, the distance from this slit to this first order maxima is different than the distance from this slit to this first order maximum here, and the same thing on the other side. This distance difference that the light has to travel is exactly one wavelength. Okay, so since it's exactly one wavelength difference in distance, that means that the waves are both in phase and they constructively interfere. Okay, this gives another visual of this, just showing the waves propagating out. Once again, this is the zeroth fringe. This uses an elm or an N. In my equation below, I use an elm instead. So this is your first order maxima and your second order maxima. Okay, so N equals 2, N equals 1, N equals 0. Once again, we'll use an elm instead of an N, but these values for elm are just integrals of 1, 2, 3, 4, and so on, however many orders we can get onto that screen. All right, so let's go through a couple of terms here. The center of the screen, the length is the same for both light beams, creating a region of constructive interference. So this is the zeroth fringe. So this is right here, the zeroth fringe is M0. The distance from there to here and here to here is exactly the same. When waves are out of phase, a region of destructive interference creates a dark fringe on the screen. That means that this first dark right here and here, the difference, the path length difference, is exactly half of a wavelength. Okay, so here's what happens then. Once again, if we place our waves here, this first dark fringe, this is half a wavelength. I know it says wavelength in there, but this is a half a wavelength difference between here and this slit opening and this dark fringe. We get to the constructive interference patterns. The first order bright after the central maximum, this is exactly one wavelength difference between these 2 points. Okay, so what we can do then is we can simply draw a triangle. If we consider this to be our first order maxima, so we have our zeroth fringe here, we have our dark fringe here, and we have our first order maxima here. If we trace these lines out, we end up with a triangle that looks like this. This theta here, and one thing is going to be, once again, this is going to be kind of hard to understand. We're looking at a picture where it looks like these slits are really far apart. These are tiny, tiny distances between these slits, okay? So what happens is this angle here, and if we trace a triangle from the center up the screen and back to the center, the angle inside that triangle is almost the same as the angle of this, okay? I know we would be using tangent for adjacent and opposite. Here we're using sine, but these are going to be very, very small angles. And when the angle is really small, tangent and sine are approximately the same. Okay, but if we look at this triangle here, we have the opposite side is here. So remember, the opposite side is the path length difference. And at the first order maximum, this is one wavelength. So this is your opposite. This is the hypotenuse of the triangle, and this is the distance that occurs between the two slits. Okay, so we can write a trig function and say that sine is opposite, which is a wavelength, over hypotenuse, which is the distance. Or we can rearrange the equation and make it look like this, where it says d sine of theta equals elm times wavelength. Now, once again, this elm is your orders of maximums. So for the first bright past the 0th fringe, this is just elm is 1. If we want the second bright, that one's going to occur up here. So now this difference right here is 2 wavelengths for this side of the triangle. So we would simply say 2 times lambda for the opposite side of that triangle. So sine of theta equals the fringe number times the wavelength divided by the distance between the slits. Okay? All right. So basically what this is doing is Young's double slit experiment basically acts as 2 individual point sources that are very, very close together and showing their interference patterns on the screen. Okay, so we have a point source here and a point source here. We get these regions of the central bright, the first order maxima, second order maxima, and once again, however many we can get on that screen is depending on the distance to the screen or the angle and the wavelength. Okay, all right, so moving on here real quick. If we use a monochromatic light source, we will get these regions of maximas on the screen. So if we just use green light, we will get several green light fringes on the screen as a result of this. If we use white light, our central maxima will be white, but notice the violet is towards the middle, and then it separates out into its regions of the spectrum. So now we have, we can disperse light due to diffraction, just like we can through refraction. Okay, so now we have our bright fringe, the violet end is towards the middle, and the red end of the spectrum is going to be spread further out. And it makes perfect sense according to this equation. If we look at this equation, we get a longer wavelength, and that's proportional to the angle. So if red light, 700 nanometers, we're going to get a larger angle of diffraction than we would for violet light, because violet light's 400 or 450 nanometers, and we would end up with a smaller angle of diffraction. So once again, you got to keep your terms straight, because this is diffraction, this is not refraction that we're talking about. So if we increase the intensity of light, this is going to have no effect on the distance between the 0th fringe and any of the maximas and minimums. The fringe simply gets brighter. Okay, so you know I like asking those types of questions. Now, what does affect it is several other things. The distance between the slits will affect where the fringes show up. The wavelength will affect where the fringes show up. Now, I've given this second equation here of x equals m lambda times L over d. I will show you on another sheet of paper where that comes from, because it is kind of confusing. But once again, we can map this out. This is the distance to the screen, so this is L. We will use the distance to the fringe here as x. And if we say tangent is opposite over adjacent, that's going to be tangent of theta is x over L. But since this is such a small angle, we can also say that tangent is equal to sine. So we can say sine is x over L. And if we set these two equations equal to one another, this is an approximation. And you can actually utilize it. I will let you guys get away with this. The AP actually allows you to use this as well. But it's not on the equation sheet, so you guys are going to have to know that. So anyway, we can approximate and set both of these triangles equal to sine and use this approximation equation. All right, let's see what else happens. Okay, real quick, I'm going to go through this and I'm going to talk about it here in a little bit with some with a simulation, and we'll see if I can get that to work. Even on single slit diffraction, even though we are saying that we're saying that it results in a perfect circular wave, there is some interference that occurs on the fringe. Okay, so what happens with this is now we just use the slit width, it's not the distance between the slits. So when the slit width is equal to the wavelength, then we should just have perfect circular wave. But if we get just slightly bigger than that, there will be interference that occurs on the fringes. Okay, so now notice the equation does not look that much difference, but we're using a W for the slit width, but there is a big difference between this. Instead of calculating the maximums, this equation actually calculates the minimums. So, and the reason for this, even though we're using the width, what we have to do is treat this as a couple of different point sources. So really what we're doing is measuring from the middle to here to get the bright fringes instead of the entire width. So the way the formula works is it actually sets up to measure the minimums because we're using the entire slit width. We could derive this out, but it's not worth it. So just remember it for now that for the single slit calculations, this is measuring the minimum, and for the double slit calculation, this is the maximum. Okay, so what we get here is a fringe that is much brighter in the center, and we get these secondary brights that occur out here, but they are very, very, very small. So when we're drawing and sketching these out, we should see that the difference between a single slit and a double slit, this central maximum is the primary constructive interference point. We do have some secondary ones out the side. As we bring the slit in closer together, it should make sense that the maximum widens out and the secondary fringes almost disappear. So what happens is, as this gets closer to the wavelength of the light, this continues to spread out, and we have very little interference patterns that result on the fringes because it's propagating outwards as a circular wave. Okay, so comparing colors. Once again, if we have violet light, notice that the fringes are going to be closer together, just like what happened with the double slit when we were talking about all of the colors of the spectrum. And if we end up with a longer wavelength, then this is going to spread out even further. Okay, I will show you guys some examples of this stuff later on. This is an example of interference and diffraction that's occurring through a circular object. So what's interesting about this is, imagine just, and it would have to be a smaller object, but just imagine having light shining on a penny, okay? And you have some distance from the penny to the screen. What will actually happen is, on the opposite side on the screen, you will get this interference pattern where there's a central bright. So light bends around the penny and creates a single bright spot back behind it. Vice versa, instead of having an actual barrier here, have a circular opening as a result instead, and you will get the circular waveform that forms constructive interference in the middle, and you will get these rings that form around with your constructive, destructive, constructive pattern, and so on as it goes outward. Okay, I'm going to stop this video, and I'm going to start another one on just showing you guys a simulation real quick, okay?